time to start. So, hi everybody. I think it is our pleasure to have you today. Although the weather is not that nice, especially we have hail and cold rain in the afternoon. But we really appreciate about our arrival. So we have a special guest from the Hong Kong Polytechnic PhD candidate Zhuojun Nan today to talk about the traveling fire and also the AI applications in the structural fire disciplines. So welcome her, and you have the rest of the hours. Cool.
Okay, thank you, Vivian, for your introduction. And so again, my name is Zhuojun Nan. You can just call me Nan. And I'm a PhD candidate from the Hong Kong Polytechnic University. And I'm very glad to present here today. And thank you for invitation from Dr. Atif Alihan. And also, it's really my honor to give a presentation for UC student SFPE chapter. So today, my presentation will talk about towards safer building, an integrated approach for structure fire analysis, design, and collapse prediction. It's a big title, but today I'm not going to go too deep through about technique issues, and I will just want to introduce you, have some feeling about traveling fire models and how to generating database for AI application and this kind of stuff. If you want to know more detail, you can go through the papers. And before we start the presentation, I want to introduce myself again. So my background is in civil engineering, and I got my master's degree from the University of Edinburgh about the structure and the fire safety engineering. And after that, I worked for Arab in Shanghai as a graduate structure and fire engineer around 2 years. And for my PhD research, focus on structure fire behavior analysis, traveling fire model application and develop, and also application of AI stuff in fire safety. If you are interested about my research, you can feel free to contact me via email or follow me in social media. And just before I arrived in New Zealand, I just finished my around 4 months exchange in the University of Queensland, and we conduct some skilled open plan compartment fire test. And this test will also used to analyze the traveling fire behavior later. And so today, my presentation will include 3 parts: background and introduce about the traveling fires, and also talk a detail about development of analysis framework for structure fire in performance-based design. So let's talk about why structure fire analysis is important. Although we already know all the structures may hopefully it follows the code and meet the requirement for the fire resilience rate, but some fire-induced structure collapse still happens and cause the disasters. For example, the most famous one, WTC Tower fall down, and the Winchell Tower, and also like the Faculty of Architecture building at the Delft University of Technology. It's the fire ignited by the coffee machine and burn for hours, then caused the partial building collapse. And after it collapsed, this building cannot be used anymore, so it has to be demolished. We all know the fire and the structure collapse will cause a lot of deaths, and also like this kind of building cannot be continually used, so it will also cost a lot of loss of money. So that's why it's very important that we should give more attention about structure fire design. And let's briefly talk about how we're doing structure design following code nowadays. So in codes, we will just simply isolate the single element, structure element, like one beam and one column, and we just throw it to the standard fire furnace and keep burning it, heating up it. And usually we will choose load bearing function as the fire resistant rate for the structure elements. And let's assume we have an entire building, and we assume the beam, the fire resistant rate is 2 hours, the column is 3 hours, and we put it to burn the standard elements to burn, and okay, it's standard fire, standard like 2 hour fire at least. But imagine if we put them together, will this entire building still can stand up for 2 hours or 1 hour, or even just half hours? It will be quite different because we're testing the single element, isolated element, but we want the entire structure still can stand after the huge fire. So how long is enough if we just use the standard fire to test it? And it has some limitation. After it, we know like the standard fire is developed due to the furnace, and it's just keep heating. It's not care so much about the compartment issues, and it's not have a cooling phase. So the parametric fire curves also will be used for the structure and fire analysis. And it's already improved a little bit. At least it have cooling phase, and it will consider about the compartment size, opening factors, and the material used, like the walls, the ceilings. But it still gives a uniform temperature distribution inside the entire compartment, and it's only could be applied in the small compartment. So it still have a certain limitation. If we really want to use this kind of temperature curve in performance-based design with open plate compartment, it looks not a proper fire scenario we use to do the analysis. So how can we improve? What did we learn already from those fires? So this kind of standard design doesn't guarantee a safe building environment. It still let some structure collapse after fire. So we should learn from the disasters. And what's the existing challenge to structure fire design to structure fire safety design? And so as I mentioned, I work for Arup and as a structure fire engineer. It's really painful for my work life because structure fire engineer need to communicate with structure engineer, need to communicate with fire engineer, and they don't know each other's back knowledge, and it's very, very hard. And in the industry, in company, you can easily find structure engineers. They have a very good knowledge about structure response. And you can find very good fire engineer. They have an expertise about fire dynamics. But as structure fire engineer, it's very hard. So let's see why it's so hard. So in the real project, when we need to apply for performance-based design, it will be like landmark projects. It's huge, it's big, it has thousands of elements you need to do the analysis. And about the fire, it's unpredictable, and it's definitely not like uniform temperature curve. So when they combine together, it makes the analysis extremely hard. And also, as a structural fire engineer, you need to know how to use software for finite element analysis. And at least you need to have a very basic knowledge about fire models and about the thermal property of structure elements as for the construction materials. So sometimes it's very hard. So the thing is, I doing literature review and I'm doing work, I realized, okay, there still have some gaps. And even the software we use, it's lack of communication, so very hard to use them together. So that's why we already observed the fire spreading in the real fire incidents and caused the fire-induced structure collapse, and the traveling fire will have an effect on the structures. Here we talk about traveling fire. It's basically the fire observed is traveling from the open plate compartment and caused the fire spreading. And in the past 30 years, there are more than 10 full-scale large compartment fire testing have been conducted to investigate the traveling fire behaviors and also the effect of traveling fire on surroundings. And based on the observation and the investigation, the traveling fire models has been proposed. So it's include the Califton traveling fire model, and also later traveling fire methodology proposed by Professor Gammelring's team, and later the extended traveling fire methodology framework has been proposed by Dr. Xu Dai, and those models has been researched many years and try to apply it to the real projects and will be hopefully will be included in the code in the near future. And today, we just will focus on the ETFM framework and discuss about how to apply it as a per fire scenario to do the structural fire analysis. And this part of work is like the continue on my master dissertation. So let's see what's the extent the traveling fire methodology framework. First, it's just combined localized fire model and the zoom model and make the localized model traveling. So local for the near field, we choose Hasami localized fire model as a near field. And for the far field, we choose the firm zoom model as to assume the effect of smoke. And once it starts to traveling, we can see if we want to analyze the steel beam, it will experience 3 different phases per hitting by the far field by smoke first, and then directly exposed to the fire. Then after the fire travels through, it will start to cooling. So now we have a very basic concept about the ETFM. And now I will try to apply the ETFM and design some traveling fire scenarios and apply to a simple 3D structure model and use it to do a lot of parametric study and see what's the different traveling fire with different fire spread rate, fuel load density, openings, for example, like this, and also different structure designs, and see how the structure will respond to the traveling fire with different key design parameters. And why we design the compartment like this way is like a slice of large compartment. You can imagine this compartment have infinity wides, and it's just fire traveling through these 3 bay. And we try to observing the fire spreading. So here we can see once we decide the key parameters of traveling fire. So in the ETFM, you have 4 key parameters you need to decide. First is fire spread rate, and also fuel load density, and the HRPUA, and also inverse opening factor. And all these 3 parameters is relevant to each other. So when you decide the fire spread rate and you decide the fuel load density and also the HRPUA, according to some rules like the Eurocode, we design this scenario based on typical office buildings, and you will get a constant heat release rate of this fire, and this fire will traveling, basically spreading with constant fire size and with constant fire spread rates. And this is the thermal response of different beams. You can see here, this is a beam 1 in Y direction, and correspondingly, here is the beam 10. After the, with the fire traveling, you'll see obviously heating and cooling circles caused by the traveling fire. And for example, we have a Y beam 7 here. You can see it will go through 3 phases. First, preheating with the smoke, and then fire approach to the beam. It has a peak temperature, then the fire passed, and it's cooling down. So this kind of high temperature received by the steel beams, I was designed on purpose to challenge the structure to failure. And let's see under the troweling fire how the structure responds. You can see from this video, when the fire travel to each bay have its largest deflection, and it's correspondingly travels through, and it have the largest deflection. And after the fire traveled, its entire structure has been cooled down a little bit, and the deflection decreased due to the cooling. And here, because this structure has been designed a little bit different. So for the first bay and the third bay, we have a shorter primary beam. The length is 7.5, and in the middle bay, it have a largest primary beam, have the length of 8 meters. So that's why we can see here, the second bay have the largest deflection during the troweling fire scenarios. And so this kind of behavior let us realize the structure response on the troweling fire not only affected by the troweling fire itself, it's also affected by the structure designs, like the layout of structures. And let's see what's the difference if we apply for different design fire scenarios. This is a structure response on the troweling fire, and then it's the structure response on the standard fire. You can see on the structure fire, the entire structure start to fall down once we start to heating all the elements, and the failure time is much more earlier, and the deflection is much more larger. It's like 5 times larger deflections. So the structure response is totally different when you apply to different fire scenarios. And go further, I also designed a lot of different fire scenarios, and let's see what's the difference. So we choose the standard fire, and we decide the different parametric fires, like the short hot, and also the long cool, and also the parametric fire with exactly same opening size with troweling fire scenarios. And we can see here, because we just choose one element, you cannot see it's like a big difference between the structure, between the thermal response of Y beam. But I need to mention, if we see all the elements, like all the beams, it will be gonna to different, because the parametric fire and the standard fire is uniform temperature distribution as the fire boundary for structures, but the troweling fire will cause the non-uniform temperature distribution. So it will have a different phase, and it will have the heating and cooling circles. And let's see here, the deflections, which we choose like as the main characters to determine whether the structure failure or not. Under the standard fire and under the parametric short hot and the corresponding parametric fires, the structure is already full. So you can see the Y beam already fall down. It's like uncontrollable deflection. But on the troweling fires, it's still quite okay. It's the deflection is not that large, but that not means structure fire is not like the worst design fire scenario as we expect at the parametric study. It's because we can see here, even we try to use the parametric fire, it will have a rapid temperature increase, but it might make our design more like overly conservative, and might leading to the potential misdirection for our structure fire design and increase the construction cost. And so as a purpose, when we're doing the structure fire design, we want to include as much as different fire scenarios for the design, and then we can decide, okay, which kind of fire scenario might be the worst fire scenario, could trigger the structure collapse, and then correspondingly, we're doing the proper fire protection design for the structure. So that's the purpose of this kind of research. And after we talk about the traveling fire models and we see the application of ETFM, and let's see why we should still continue doing the large scale fire testing in the open play compartments. And as I mentioned, there are a lot of different fire tests that has been conducted. And we can see here, the fire always spread rates with different fire modes, like constantly traveling, and the fire keep growing, and the fire spread rate increase, the fire size increase, and increase suddenly, zonal intense burning happens. And maybe sometimes the fuel load has been burned out. It's caused the fire decaying. But here, the zonal intense burning, maybe you are not that familiar with it, because in the small compartment, we will call it like a fully developed fire. But in the open play compartment, it's hard to make the flashover happens like the big compartment, and you just have a significant amount of fuel in specific area. So it might just cause the zonal intense burning. It will not cause the flashover of the open play compartment. So this is a term we proposed to describe the fully development fire in open play compartment. And as we observed in the real large-scale fire testing, the fire always spreading with different modes, and we choose the velocity of burning rate, like the velocity of burning front, and also the velocity of burn out front, and based on the fire spread rate, and we can determine the different fire modes, like constantly traveling fire, growing fire, and the zonal intense burning, and the fire decay. And we summarize the relationship between the fire spread rate and also the fire size. We can find out once the fire is not that large, significant enough, it might traveling constantly with the constant fire spread size and the fire spread rate. But once like some situation changed, like opening changed, and the fuel load density changes, and the fire size getting increased, and also then the fire spread with much more larger fire spread rate. So it's always influence each other. So that means when we develop and want to try to apply our traveling fire scenarios, we need to think about what kind of fire spread rate and the fire size we want to use, we want to design, and also need to consider the relationship between them. So that's why it's like two parts. I already get once we know like the fire not spreading constantly in the compartment, and let's see how can we improve it and give the engineers, give the researchers more flexibility to adjust their design traveling fire scenarios, and then could to apply to structure fire analysis in performance-based design. So we already have existing traveling fire models, and basically they just choose one single localized fire model, and it's just can used with constant traveling fire spread rate. But, and even in the fire test, it's only used the uniform fuel load distribution. It's followed our design, because when we design the fuel load density for the buildings, we just assume all the fuel load is uniformly distributed in the room. And then all the fire test is designed like this. But should we consider about the fuel load distribution with more reality? Like, for example, in a living room, you might have a sofa, you might have a timber table, and it's burnable. And then fire happens, it's not like gonna to traveling with uniform fuel load distribution. So we also conducted full-scale wood creep fire test with non-uniform fuel load distribution in Sichuan as part of Fire project. And this kind of test, we aim to investigate the non-uniform and the discontinued fuel load distribution to investigate the fire spreading behavior and their impact on the surroundings. So I will just choose one test and show you the observation. So we ignite the first wood creep, and then waiting a little bit, it ignites the second one. And you can see here, the difference between the first one and second one is just the spacing between the wood sticks, and it's already caused the different local burning behavior. For the first one with small spacing, the fire size is small, but the fire duration is longer. But for second one, the fire burning more tensely, so it has a larger fire size, but burning duration is shorter. So even with same fuel load density, but different layout of fuels, it will also cause a different burning. And here we can see, like different with the constant traveling fire, if the fire leaping to another fuel loads, it will cause the multi-center of the fires. It might make the situation worse because now you might have the fire is also traveling, and you have a multi-centers, and one might ignite each others and affect each others. So when we consider about the load distribution, what will also affect the traveling behavior? So local fuel load density and the porosity of wood creeps in our test, and the gaps between the fuels. Like for example, if the gap is significantly large, the fire will not ignite the next one fuel. And how it affects on the traveling fire behavior, it will have a different fire size and the different duration of localized burning. And also for the disconnect fuels, it will ignite and with times. So this kind of wars, like it's very complex behaviors. We are very hard to summarize it very well and with like some physical mechanism for this, and it will also cause the unknown failure. So in here, it's like we need to develop the traveling fire models a little bit, and we should consider about the localized fire burning stuff, and we also should include the traveling behavior models to the traveling fire models. Then we can describe and represent the traveling behavior better. So let's review a little bit. First, we try to use the time temperature curve to do the structural fire analysis, but it's just suitable for small compartment, and it just gives a uniform temperature distribution. Then we improve a little bit. We try to include the localized fire model and the traveling fire model to the performance-based design, but there still have some certain limitations. So for the future version, we do better performance-based structure fire design. We could establish a design fire scenario library, and we can represent the real fire development, and also we consider about the local damage, and we include the heating and cooling effect induced by traveling fire on purpose. So here we develop a new function in OpenSys. I will not call it like a new traveling fire model, but it's a new function. We will include different localized fire models like airport, ceiling jet, localized fire model, Hasami localized fire model, and also the localized flashover for different kind of localized burning behavior. And also we use different fire size and fire spread rate to represent the traveling behavior, but how can we achieve it to give the traveling behavior? We will use the external file in OpenSys. We already developed the natural file model. And if you want to input your own file parameters, you need to use the file parameters file. And it include different columns, and you can input everything you want in here, like how we can represent the parameters with a different behavior with time changes. So the first column, we put the time we want for the fire scenarios, and then we choose the different fire location. Like if you want to, it goes through by this rule, you can determine different locations. Also, you can determine the different fire size, different fire diameters, ceiling heat, and also the smoke effect, and all the details of the parameters and all the which way you want to use. You can go through my paper and you will find out the details. I will not explain in detail here. I will just want to let you know you can use this model. And also, the amazing thing is we could just directly use the natural fire to generating the design fire scenarios as much as you want in OpenSys. And we also have the Git plus OpenSys, like as the finite element structure model, and use the thermocouple function developed in Git, and combine the design fire scenario together with the structure fire analysis together. And we even can get our displacement and the gas temperature as a key parameters to get the database we might use later for AI training. So I think this part you might be already getting confused, because it's like suddenly I start to told you, okay, we have amazing software, we can do everything by once. Yeah, I think it's very painful for structural fire and engineers to doing all the simulation. You might need a lot of Excel to do and to get the gas temperature as a fire boundary you want to put the structure software to do the thermomechanical analysis. But in the structure models like UpCurves and Alcina, sometimes they are too powerful. They are not designed on purpose for structure fire analysis, and it's very hard. You need manually input every fire parameter and every fire boundaries for the structures, and it's very painful. But now we have this quite Git plus OpenSys as a user interface, and we develop this thermocouple. I will just simply explain why it called thermocouple. So when we're doing it, we put a thermocouple in the structure, and you can determine the location of thermocouple by yourself. Like you can choose some key location, and you put it, and you get the location of thermocouple. Then you can go to the natural fire, and you determine the thermocouple in natural fire, and it will automatically generating output the gas temperature you need. And in Git plus OpenSys, it will automatically read the gas temperature as a fire load, and then doing the analysis, then generating the database. And the good thing for this kind of framework is it's all automatically. You just need input the parameter, and you need design the fire scenarios by yourself. Then it will automatically conduct it and doing all the scenario, all the analysis. So it will not cost a lot of time, and it will release our hand and reduce our workload a lot. For example, in one of my research, I'm doing structural fire analysis for this kind of arched roof with aluminum structure beams. And I designed thousands of localized fire scenarios with 30 different 12 different fire locations and combined with varying fire sizes. And I do it, it's not like what I want to do a good design. If it's like a design, I might just choose this part, but I want just see how the fires, if it's happened in different location, and we see all the structural response under the potential fire scenarios. And so that's why I choose thousands of localized fire scenario, and using the natural fire model in OpenSys, generating all the thermal load, and then apply to the structure and using OpenSys to get the structure response analysis, and choose some key location as the monitoring points to get the database. And this entire simulation with thousands cases just cost 1 week. It's much more easier. It's not I working entire 1 week. It's just the simulation doing 1 week. So yeah, that's true. Like we don't need to calculate again and again and manually input again and again, and maybe also cause some error by some mistake. Now, like use this framework, we can get our database we want with temperature information and with displacement information. And let's see how can we play with the database. As I mentioned, I'm doing this kind of simulation and I want to use it to see how the structure responds to different fire scenarios. If we got an arch, like as a very experienced structure engineer, we just maybe, even me, I will think about, okay, maybe the structure is just fall down after heating. But in fact, it's different. When we heat up the structure with localized fire, it will be upward deflection first because of expansion of element beams. And then some single components close to fire start to buckling. And with some buckling, it might cause the partial collapse. And then if the fire continues and increase, it will cause a global collapse. But sometimes the global collapse of the entire building is not just directly happens without a partial collapse first. As we can see here, if we put the localized fire in the lower part, the global collapse will suddenly happen with no signs in advance, like a partial collapse. It will cause much more risk for us to predict the global collapse, and it will give no time for firefighters evacuate from the building before it collapses. So this kind of thing is a funding after we doing the analysis for all the scenarios. And this is a good start, and we want to continue and doing more analysis with different, like more traveling fire scenarios and see the difference. And also, as we mentioned, we can also use it. We use the database to do the rapid forecasting of structure collapse in fire. And here we choose LSTM as a machine learning training model. But I will not go through very detail how we choose and we design the architecture and the layout of the machine learning model. I just want to show you like why it's important we're doing the simulation and have a doable framework to getting the database. So not like the internet, like the ChatGPT developed very well recently, we can easily get a lot of data from internet. But for structure fire, it's very hard to get a lot of database and good database for training. So that's why it makes the training database more important at the very beginning. Try to use it to train the machine learning model. And also, it's very important for the machine learning training if we want to increase the database and the prediction results should be better. But sometimes we will just think, okay, we got all the information from this just simple structure, and we put it all as an input to training machine learning model. But that means how can we continually increase the database? How can we continually increase the amount of training? So that's not a good way. So we propose a modular AI training system. Like here, we will just get 3 sensors as a key monitoring points, and we get the deflection and the temperature in these 3, and each one will use as a module training, like with AI model, the data from this sensor and the training and doing the prediction, and another sensor training and doing the prediction, and the third one also the same. And then we try to make them connect to each other, communicate with each other. Okay, like the first one told, okay, I predict one collapse, and about the second one said, okay, there is nothing happened to me, so maybe it's a fake warning. If they are 3 all predict, okay, it will be a collapse later, then we can determine, okay, it might be the true collapse, and we need to give in the warning now. And this kind of work will combine with a smart sensor, like the wireless smart sensors, and with the 5G techniques, and used to the real induced fire test gonna to conduct in later this year in China again. So let's quickly doing a summary of my presentation today. So first, we observe the fire-induced collapse even in modern building, which follow the design code. And we still realize that the fire could still induce the structural collapse. And we just apply the constantly traveling fire scenarios. We already found out it's very different structural fire response compared to the standard fire and the parametric fire. So that's why it's very important we should include the traveling fire scenario to the performance-based design doing the analysis. And then we know in the real world, the fuel load never distribute uniformly. So we also conduct some large-scale fire tests and doing more further investigation how the fire behaviors will affected by the fuel load distribution. Then we develop the new natural fire model function in OpenSys, and it could represent any fire scenarios you want to design. We establish the design fire scenario, and we use the Git plus OpenSys, connect the design fire scenario as the fire boundary as input to doing the later structure fire response analysis, and automatically generating all the database we need. Then we applied to do the mechanism of fire-induced structure fire failure in depth. And also with the machine learning technologies, we can doing the prediction of structure collapse in fire. And we also plan to do it, use all the database, and with some new technique, we can doing the smart structure fire performance based design in the future. And here is the reference list, and also if you're really interested and you want to go through more detail, you can find all the information in our publications. And thank you for listening. This is my presentation today. Thank you.
Very much. It is a very wonderful presentation, and which shows us the recent research in terms of traveling fire, and which the corresponding information we haven't been really understood in that deeply in terms of globally and also in the New Zealand context as well yet. So thanks, Zhuojun, and once again, thanks for your presentation. We actually get a lot of information in both traveling fire and AI application. So now it is the great question and answer time. So if anybody would like to ask a question, please feel free to do so. And also for people who are online at the moment, you also feel free to propose the questions in the chat box.
Questions?
So, no, great presentation. I'm Gordon. I'm also a PhD candidate, and my interest is in the response of steel buildings under fine conditions. I've got two questions. It seems like this is for unprotected steel or unprotected metals. Is that
Yes.
a correct assumption?
You mean like this framework
Yes.
or this? You can just simply add the fire protection. We'll also develop the fire protection material in Git, in OpenSys, and you just input. It could be doing the analysis for the steel structures with fire protection.
Right. So your I'm not exactly sure how your AI model works. I'm not even sure if anyone really understands all the nitty-gritty apart from input and output. But so your AI response, you would need to tell it, okay, so I've got this steel structure or this how I've laid it out, I've got my members in this way, and each member has this amount of protection, and currently, or you have trained it to look at different protection thicknesses and everything as well. Is that?
Yes. So for the AI training, I will go a little bit further for the AI training. Okay. For the AI training, the database input is the gas temperature from the fire, and also the displacement from some key points, like this connection part. And this is all the input for the training as a database. So that means when you're doing the prediction, you also need to get some gas temperature from fire, and also need to get some displacement in the real time as a feed to doing the prediction. And the output of the prediction is a displacement of like one connection. So the output is just the future displacement, and the input is a real-time gas temperature and the displacement. And we also need to give some standards to determine whether the structure collapse or not. So we use like 0.5 meters as a standard. If this connecting point fall down like 0.5 meters, it could be determined as failure. And if also 3 reach to this, we will say, okay, entire global structure is failure. This is the thing, because sometimes I know it's a little bit confused when we talk about the input and output for machine learning model. Most of people will just think we get the real-time gas temperature. We get the real-time fire scenarios. It's enough for the input as a machine learning model to do the structure fire prediction. But as we know, like the structure response is very complex, and it's relevant to the structure itself, like different materials, different section and everything. So also it's very important we need to put some information from structure and to correct the prediction of machine learning model.
Okay. Thank you very much for that.
Okay.
My second question is, because I'm not personally used overseas, if you go a little bit forward, I think this is your summary slide.
Yes.
In animation on the bottom right. That seems a bit dynamic to me.
Yeah, we use dynamic analysis. We use dynamic in-plate analysis for this. So you don't need to just ignore after it's fall down and it still have dumping. It's because of the simulation. It's not a real structure response. So the structure response will need to cut down after it's fall down, the first time fall down.
Right.
But we use the dynamic analysis, it's push the simulation continually running, and it will have caused some damping just because of the numerical simulation stuff.
So that animation start right before you reach your failure time, is it?
Yeah,
I see.
yeah, I need to update this animation. It will stop after the first fall down, like this part, this moment, it should be stopped.
I'm sorry, yeah, because I must have misunderstood that, because it seemed to me that it might have just been from initial start and then suddenly items with temperature and then it falls down, but thanks for clarifying that.
Mm,
Thank you very much, Tom.
no worries, thank you.
And great presentation. Could you let me know what sort of elements you use to simulate the response?
Element, you mean structure
Yeah, like
elements?
what structural elements did you use? Like,
You mean which part? So I for use different elements, it's like basically 2D
no, I want to use the element type. Element. Oh, yeah.
beam element. It's like just 2D beam element for all the structure members.
I
Like,
mean, like beam with fiber sections, concentrated plasticity. So how does the fire interact with the structure?
I don't follow. It's like, it's not a fiber elements. It's like a 2D beam element. We choose the different type of element for the thermal analysis, like Team Cinco or Thin beam. Like this kind of were quite normally used in structure finite element structure analysis, but we change the thermal property. We give the thermal property of the structure materials and then make it change with the temperature and recording and doing the analysis, recording to the heat transfer analysis results. So the element is not that difficult, or it's not that unique to define. It's just very basic finite element type used for analysis. We don't use the solid 3D element to do the analysis. It will be very hard to do the global structure response analysis. We just simply use the 2D structure elements.
Okay, I also have a question. So I see like the overall analysis methodology shows like a great potential to maybe use the AI to replace the human calculation in the future to tackle with the traveling file problem. However, do you believe that the current tool or the software package is ready for a simple engineering designs? If I just want to say maybe very simple open plan compartment and for a traveling file scenario, or do you think it still needs to be further developed, and if it needs to be developed, then which particular aspects needs to be put as a priority list to be tackled in the next step?
Yeah, I will see, like, as I mentioned, the TFM proposed by Professor Gamorin's team, it's already applied as traveling fire scenarios in some real project in UK, and it's done by Arab. So I think this kind of traveling fire models is ready to apply to doing some analysis, give you a very beginning try to see how the structure responds to the traveling fire scenarios. But as I mentioned, we need to consider more about energy balance, the relationship, consider about the different fire size and the different fire spread rate, how to infect each other. You cannot like just, okay, see, I have an extremely big fire, but it's like slowly traveling. It's not possible. So we should also consider more about the fire dynamic and how all the all the factors affect each other. So maybe we still need conduct more large scaled fire testing and to exactly know the fire dynamic inside the open play compartment and how it affects the fire spreading behaviors. And we can also use this kind of knowledge to improve the traveling fire model. And hopefully we can apply it later.
Okay, thank you. And I also have a second question because I see the fancy experiments conducted in the Sichuan laboratory, which I think it is more of like the real experiment facts that I see about the traveling fire. However, is there any like the novel findings or like any unexpected things that were observed in those of the real experiments compared to the any of the analytical models so far?
Okay, you mean this?
Yeah, so like I think it's called X1 compartment experiment.
Oh, it's not
right?
in Sichuan.
Oh, okay.
X1, X2, it's also conducted by Professor Gammarin's team. It's X1 and X2. I think it's conducted in Spain. And even recently, they have a called the large scale fire experiment called the Cold Red. It's with timber ceilings and the fire size could reach the hundreds megawatts. So always we can observe something we unexpect in the traveling fire. I think we can go back to. Sorry. This part. So there are a lot of different fire tests and in the past 10 years. And you can see even like 4 of them design very similar. It's Edinburgh Tall Building Fire Test and the Merivale and the GFT test. They are quite similar, but just change the fuel load density. And you will see all the traveling fire scenarios changed. The fire behaviors changed. And compared to the others, it might have a different fuel load density, different compartment size. Even further, it's like, should be not in here. Another fire test is even have a circling traveling fire.
Oh, the Shudai model.
Yes. So we conduct large scale fire tests. It's like to simulate more real fire scenarios and get more sense about the fire behaviors, and all the recording data could try to help improve the traveling fire model. That's why they spend money to do a lot of large scale fire tests and try to summarize all the data together and see how the fire behaviors could be summarized with like simple equations and we can use.
Thanks so much. Does anybody also have a question you want to ask? Can you go to the next one? So were you comparing like the curve from different different fires, different fires?
Okay.
Yes, this one. So on the right hand side, the deflection, right?
Mhm.
You said you will design the beam based on like the worst scenarios. So which will be the standard fire curve? Oh, sorry, the current.
Yeah, it should be the short hot parametric fire. But it's very hard to see is this one already the worst one.
Yeah, because you said it's conservative, that standard fire curve, but you want to design it.
Sorry?
Like on there, you said standard fire curves to be overly conservative.
Yes, so it's like overly conservative is not a good design. Yeah, so like sometimes we hit it immediately, and of course the structure members will immediately failure. But after we design, we need to do recalculation again, simulation again. So we need to consider about the fire protection, and the fire protection will stop the heat transfer inside the structure members a lot. Then will totally change the thermal response and the structure response. And then it's hard to see like we really need to consider this kind of fire scenarios, or this kind of fire scenarios really follow the compartment size, or like it cannot be used like in everywhere. So that's why I mentioned like with the framework, you have your own freedom to choose, and based on your experiment engineer judgment, you can decide, okay, maybe this kind of fire is over conservative. We don't need to use it. And we could compare the standard fire and the long cool fire, maybe more suitable. And then we're doing the analysis and we see whether the structure fire design is good or not.
Is there any consideration for some bounds between when you would consider with a standard or those shorter parametric fires would be appropriate? In terms of area and ventilation factors, there probably would be two main parameters. At some point, as the compartment gets small, like for example, this room, it would be reasonable. And as the compartment gets larger and larger and ventilation changes, that assumption becomes increasingly less accurate. Where's that transition point?
So the transition point, I remember, so like the compartment fire, let's see, the parametric fire have just here. So it's already defined very well in the Eurocode. It's give you a lot of limitation. If I remember correctly, for the parametric compartment fire, the compartment size should be less than 200 square meter.
Okay.
Yeah, so it's not suitable for open play compartment anymore. But like as we discussed a lot of times, in small compartment, we don't need traveling fire.
Yeah.
And in open play compartment, we cannot apply parametric fire. That's why we need to consider all the fire scenarios, and we need to design it very well to suit different scenarios.
Also, you can show that where you have a relationship with the velocity, but not velocity.
Oh yeah.
That will define which one is better.
We lost it. Yeah.
I think this equation will tell you which one is healthy fire. So we have to room you can consider. So if the burnout velocity is higher than the spread velocity, there's some bounds, some figures suggest, so which tell you which one. If the room is big, if the velocity is like this, so you can say it's a healthy fire. Otherwise, it's a, like for example, zonal intense burning, or you can say localized fire. By velocity, you can define the size.
Yes.
And we only did, like, we can only consider 2D structures. Is that like
No, like 2D beams is like structures is always 3D structures,
Yeah.
like. Let's show here, maybe. So this kind of structures is always we designed like 3D structures, and only the beam we use the 2D beams. What means 2D beams is like we're doing just heat transfer 2D sectional, and in the length direction, we just calculate based on the relationship. And the 2D elements, we not use the 3D solid finite element to doing the analysis. If we try to use in 3D, it will be like even in the 2D sectional, the section of the beam, the heat transfer will start the one mesh of the I-beam and to another mesh and to another mesh, and that's called the 3D heat transfer inside the beam. But we don't really need that specific for structure fire global analysis. So we just simply choose the 2D elements. It means this element is a line. You need to define the start point and the end point, and then you need to decide the I section or H section and the section you want. Then it will generating the entire beam. It's not like 3D solid elements with a lot of small mesh, and you can do the finite element and the heat transfer inside the structural elements. So that's why it called 2D elements. It's not like the entire structure is 2D.
I also haven't seen any questions from on Zoom. So if nobody would like to ask more questions, I would like
I
to.
have a practical question, sorry. My name is Flavie Georgis. I'm currently practicing fire engineering for 50 years. Back to this example where the animated picture was there. If you do all your calculations and reach this conclusion,
Mhm.
what are you gonna say to the client?
Well,
How are you gonna advise them? What to do?
the client is like, let's go back to here, okay?
But
So,
you reach this point, then
yeah. So after I doing entire analysis, if what I suggest to my client, the codes will require you protect all the elements. It costs a lot, right? But after we doing so all the analysis, we will find out only this kind of part when the fire happens, it will cause the fall down. Even here, it's with very high ceiling heights. Even the fire will have a 40 megawatt, it will not cause a significant effect to the ceiling. So I will just suggest my client, you maybe just protect part of the roof is safety enough. And it will be a more cost less design, and it will reduce the construction cost. You just need to put fire
so
pressure here.
selected members to be
Yes.
protected.
Yes. Yeah, we
And
just,
that is the cost saving.
yes. Because we already do the analysis and we prove, yeah, like if the simulation is perfect, there's no error and it's good enough, we can tell clients, you just protect some important part. You don't need to like exactly follow the code and protect all the elements. So that's why sometimes for the large space structures, the clients ask us to do performance-based design to save some money, to reduce the cost. Of course, we make sure it's safe first.
Okay, and that is calculated based on the losses for the building?
Sorry?
I mean, that decision that you come up across at the end is just to protect 1, 2, 3, 4 is calculated against how much loss he would have if he wouldn't do it. Because that to me is like a roof, right? So if the roof collapses, what's the problem?
Oh, it's just a
That's
one
a loss
piece.
of property.
No, it's just a piece of roof. I choose it like a very simple example to do the simulation. But for example, if it's a real structure, the clients will ask us to do the simulation for this kind of structure. If one partial of this important airport this is the biggest airport in the world now, and it's have a lot of complex structure design inside. Once the fire happens, if one part of roof fall down, it need to stop. It cannot to doing business anymore, and it will be a lot of loss.
So business loss.
Business loss, and of course, you can imagine how many passengers inside the airport. If the roof is just suddenly fall down, a lot of people going to die also. And
You wouldn't expect people to be there when the fire is raging, everyone is out. But the question is would your decision be different if that was a floor in a hospital? Would your advice be different?
Like the hospital, and then it's again back to hospital, we might not really do the performance-based design. We exactly follow some rules. It's like some part we could do performance-based design. We just try to saving some construction money, but some particularly like a hospital and the important part, we might not like the commercial building and not commercial residential building. We'll just maybe follow the core code. It may still quite save your money.
Any more questions? Okay, cool. So if it looks like almost the end of this presentation, and once again, I would like to invite you to give applause to the Zhuojun and thanks for The rest of your journey in New Zealand will be wonderful, and hopefully you have a memorable journey
Thank you.
for the rest of the time.
Thank you.
Thank you.
Thank you.